Yo, what is up, boys? Today is day 15 of becoming a full stack developer in 8 months, and everything's running slow. Today, probably we're going to have a shorter stream, at least in the morning, because I woke up later than expected, so that wasn't fun. And PC is still loading, so that's why we have a little bit of a slower start. But anyways, we'll go through the Odin project. Let me pull up the chat. I still don't see it. But yeah, I couldn't wake up today, so we'll see if we can do another stream later today. But yeah, alright, everything's pulled up. Seems fine. So what are we doing today? Let me see. I think it was browser compatibility or something like that. We have intermediate HTML and CSS, browser compatibility, and then frameworks and preprocessors. Cool. Alright, so let's read through this. I'm going to zoom in a little bit. So, as you continue on your web development journey, it's important to keep in mind that the end users of your work might be using a variety of browsers: Chrome, Microsoft Edge, Firefox, Safari, to name a few. And at the same time, the number of users using mobile operating system is growing rapidly. Therefore, you should also consider mobile versions of different browsers. And I'd say this is even more important because as you guys know, I have a business and most of the users are on mobile. No one is on their PC nowadays, at least when shopping. Alright, so lesson overview. This section contains a general overview of topics that you will learn in this lesson. Understand browser compatibility and its history. Know how new CSS features make their way into browsers. Know how to check for compatibility. Alright, and we're starting with browser history. The history of modern browsing began back in December 1990 with the release of World Wide Web browser. It was written by Tim Berners-Lee while working for the European Nuclear Research Agency known as CERN. It was later renamed to Nexus to avoid confusion with the World Wide Web. Nexus was the first of its kind and allowed users to view basic style sheets, read newsgroups, and even had spell check. It might not seem like a lot today, but at that time it was truly groundbreaking. The release of Nexus was just the beginning, though. As the next decade, people witnessed the first release of browsers such as Mosaic browser, which quickly gained popularity and became the most popular browser on the globe. From there, the growth of the World Wide Web exploded with releases of Opera and Netscape Navigator browsers. In 1995, the world got introduced to the first version of Internet Explorer, which became the dominant player in the market. At some point, Internet Explorer was used by more than 90% of all users. To counter this dominance, Netscape launched what would become Mozilla Foundation, which develops and maintains Firefox. Soon after that, in 2003, Apple launched Safari, and in 2008, Google Chrome was launched. You're likely familiar with most, if not all, of these names. There is a lot of competition among browsers still to this day, even though Chrome and Chromium is the dominant player in the market. So what is browser compatibility? Today it is impossible to imagine the web without the use of browsers. We have witnessed a shift from standalone applications to HTML5 and progressive web apps that allow applications to fully function within a browser. For example, Microsoft Word and Excel for the longest time could only be executed via a standalone application. Now you can utilize those applications through any browser without the need to install any files. As companies compete for market share, different browsers are using different engines to display information on web pages. For example, Chrome and Chromium utilize Blink, while Safari uses WebKit. Because of these differences, your applications may behave differently in the browser. Due to Chrome dominance, the vast majority of applications are designed to work smoothly with Chromium, providing as good of a level of performance and providing as good a level of performance in other browsers is secondary. Right? For your web development projects to have a broader reach, you must make sure that you're testing your web applications against browsers which are most likely to be used by users. Chrome, Safari, Firefox, and other Chromium-based browsers like Microsoft Edge, Brave, etc. are more common among regular users, but you might find you need to support less common ones like Internet Explorer as well, depending on the user base or the company you work for. For Chromium browsers, if it works in Chrome, it should work in other related browsers as well. Sure. Browser releases and new CSS features. W3C, the World Wide Web Consortium, is the authority behind developing web standards to maximize accessibility and consistency of the web experience. W3C is also the authority to develop new features in CSS. This is a closely collaborative approach with the web as a community, as well as companies developing web browsers. When web browsers such as Nexus and Netscape were released, there was no such organization as W3C to help create more compatibility. Your application could look and function differently in each browser. Even worse, your application could have been completely unusable. Web developers had to make specific adjustments for each browser, and not every developer had enough resources to make that work for everyone. Today, as standards around the web evolve and change, and web developers begin implementing new features in their codebase, browsers must provide support for those new features. If the user experience is impacted by a lack of support in browsers, users might find their way to a competitor or download a different browser basically. So, when is it safe to use new features? As exciting as it is to implement new features, there is a risk of rushing. It would not be a positive experience for users to find that, for example, your application used to work well in Firefox, but due to the changes in the codebase, it is now unusable in Firefox, but works well in Safari. Thankfully, there is a tool that can help you prevent this situation. Can I Use is a great resource to help you validate if new features are supported by browsers. It provides statistics on which browsers and platforms are supporting new technologies, and even which versions of these browsers support specific features. It is generally good advice to implement new features when they are supported by most common browsers. This way, you're less likely to encounter an issue that a lot of users will face. So, can I use transform, for example? And it seems like I am colorblind, but it seems like everything is in the green. Now, what was it? Will change. Can you use will change? No results. I've misspelled it. Will change. Not supported in Internet Explorer 6. Supported. So those one with the stripes are not supported and the other ones are supported. Android browsers, Opera Mobile, Opera Mini. Chrome. Alright, so it is supported by most browsers, it seems like. Baseline widely available across major browsers. Transform. So this has more compatibility even with other versions of Chrome and Edge that Will Change didn't have. Alright, cool tool. It is generally good advice to implement new features when they are supported by most common browsers. This way you're less likely to encounter an issue that a lot of users will face. Mobile browsers. Traditionally, the web and desktop computer first. Traditionally, the web was desktop computer first. Traditionally, the web was desktop computer first. So they mean that they designed websites for the desktop first and then did media queries for mobile. I had to read through this sentence a couple of times to get it. The application was successful if it worked well on desktop browsers, but as smartphones have become more popular, each year more and more users are using mobile devices as their main web-facing device. In some areas of the world, mobile users are a vast majority. Mobile devices mostly consist of smartphones and tablets. The most popular mobile operating systems are Android and Apple's iOS. As you're developing your applications, you must also consider whether your application should be fully mobile compatible. There are a couple of specifics about mobile browsers that you need to keep in mind. On iOS and iPad OS, Safari is technically the only supported browsers. Yes, you can install Chrome on Firefox and you can even set them as default, but they are not full browsers. They're still using the Safari rendering engine WebKit, therefore for your web application to work for Apple users, you have to ensure support for WebKit and other technologies in Safari. It's important to remember that mobile browsers are not one-to-one with their desktop counterparts. A project that works in the desktop version of Safari might still need adjustments to work properly on the mobile version of the same browser. Alright. Another consideration for mobile browsers is the magnitude of different screen sizes. It is virtually impossible to have every physical device available to test, and thankfully browsers provide a way to emulate other devices. The important piece to remember is that when, for example, you emulate an iPhone in Chrome, all that you're emulating is the screen size. Keep in mind that any specific considerations of the operating system will not be reproducible, which means that even though everything functions well in Chrome, when emulating a device, it could behave differently on the actual phone or tablet device. Alright, so review can I use? We've already went there and we'll read this article on browsers and iOS. Cool. Let me see how long this is. This is quite short. Can I zoom it in a little bit? Okay. So this is from September 22nd, 2020, and it says Safari is the only browser on iOS devices. I don't mean it's the only browser that ships with iOS devices, I mean it's the only browser that can be installed on iOS devices. you can install something called Chrome. MySQL coding, good morning my man, or whatever time it is for you, but hello there, thank you for tuning in, appreciate you my guy. So you can install something called Chrome, you can install something called Firefox. Those aren't different browsers. Under the hood they're using Safari's rendering engine. They have to. The App Store doesn't allow other browsers to be listed. The apps called Chrome and Firefox are little more than skinned versions of Safari. Wow, I never knew that. So if you're a web developer, there are two possible reactions to hearing this. One is duh, everyone knows that, and the other one is what, I never knew that. Yeah, so I'm the latter. What is the difference between Netlify and Shopify? Netlify is like a place you can host your files, where you can deploy your application, and Shopify is a whole builder for e-commerce. But with Shopify, I think you can host your store there, but yeah, it's more of a builder than just a place to upload your files and deploy your application. So if you fall into the first category, I'm guessing you've been a web developer for a while. The fact that Safari is the only browser on iOS device is something you've known for years, and something you assume everyone else knows. It's common knowledge, right? Netlify is free. Yeah, I don't know if they have paid versions as well, but it's mostly free. But they don't have the capability of creating a whole store like Shopify. Okay, but if you're relatively new to web development, heck, if you've even been doing web development for half a decade, you might fall into the second category. After all, why would anyone tell you that Safari is the only browser on iOS? It's common knowledge, right? Indeed. So that's the situation. Safari is the only browser that can run on iOS. The obvious follow-up question is why? And it's because Apple are greedy, obviously. Apple at this point will respond with something about safety and security, which are certainly important priorities. So let me rephrase the question. Why on iOS? Why can I install Chrome on Firefox or Edge on my MacBook running macOS if there are safety or security reasons for preventing me from installing those browsers on my iOS device? Why don't these same concerns apply to my macOS device? At one time, the mobile operating system iOS was quite different to the desktop operating system OS X. Over time, the gap has narrowed. At this point, the operating systems are converging. That makes sense. An iPhone, iPad, and a MacBook aren't all that different apart from the form factor. It makes sense that computing devices from the same company would share an underlying operating system. Okay. How much time required to make a website? Using Shopify, or you want to code it from scratch? If it's with Shopify, it can take from a couple of weeks to a couple of months, depending on how complex you want it. You can even make it in a day, but it won't be that good, it won't be complete. As this convergence continues, the browser question is going to have to be decided in one direction or the other. As it is, Apple's laptops and desktops strongly encourage you to install software from their App Store, though it's still possible to install software by other means. Perhaps they'll decide that their laptops and desktops should only be able to install software from their App Store, a decision they could justify with safety and security concerns. So imagine that situation: you buy a computer, it comes with one of the web browsers pre-installed. You can't install any other different web browser on your computer. You wouldn't stand for it. I mean, Microsoft got fined for anti-competitive behavior when they pre-bundled their web browser with Windows back in the 90s. You could still install other browsers, but just the act of pre-bundling was seen as an abuse of power. Imagine if Windows never allowed you to install Netscape Navigator. And yet that's exactly the situation in 2020. You buy a computing device from Apple, it might be a MacBook, it might be an iPad, or it might be an iPhone, but you can only install your choice of web browser on one of those devices for now. So only on the MacBook you can install any other browser for now. It is contradictory, it is hypocritical, it is indefensible. Alright, so anyways, that was a short read. It's quite interesting. I never knew that you can't really install any other web browsers on an iPhone. Okay, so we have read more about the history of the web and take a look at how the web works. Those are the additional resources, and let me just see how long they are. Alright, this one is a bit longer, but we'll read through it, and this one also a bit longer itself. Alright, sure, no worries. So let me zoom in a little bit, and yeah, that should be good. Alright, so do you remember launching your web browser to read this article? If not, don't worry, the history of web browsers started over 30 years ago and we no longer notice how frictionless the browsing experience is. But have you ever wondered where it all began? In today's article we'll dig deep into the browsing history, but pun intended, to track down the key milestones in the evolution of modern web browsers. So what was the first web browser, who invented it, who won the browser wars, why is Chrome so successful today, who pioneered tabbed browsing, and more. But before we begin, the first web browser changed the history of online productivity. Be sure to follow up on other inventions that blazed that trail. So those are other articles you can read, but we'll skip through them. So without further ado, the 1990s at CERN World Wide Web browser. Like many cool inventions, including your smartphone's touchscreen, web browsers came to life in the hallways of the European Organization for Nuclear Research, or CERN. And that's nothing to sneeze, considering CERN's other pursuits include the God particle and antimatter. Our story starts with the not yet knighted Tim Berners-Lee, a British software engineer who took up a contract at CERN in the 1980s. During his stay, Berners-Lee romanced with the concept of a system that could streamline and improve collaboration between CERN employees. I actually wrote some programs to take information from one system and convert it so it could be inserted into another system more than once, and when you're a programmer and you solve one problem then you solve one that's very similar, you often think, isn't there a better way? Can't we just fix this problem for good? And this was a quote by Tim Berners-Lee. While the original project, dubbed Enquire, hadn't caught traction, Berners-Lee revisited the idea in 1989 in two formal proposals he drafted with a CERN employee, Robert Kay. Anyways, from there, the pair moved on to develop a virgin infrastructure for the World Wide Web, a server on Next Computer, a web page, and the World Wide Web browser. Perfect. A 2019 rebuild project recreated the World Wide Web browsing experience by CERN. Unfortunately, there isn't a link we can check out, but with those three components in place, Berners-Lee released his invention to the public. with the LIP World Wide Web software package in November 1992. That was the beginning of the mostly wonderful history of web browsers. Web productivity milestone number 1: cross-platform experience. Much of the appeal of modern productivity tools lies in the cross-platform experience. Regardless if you want to edit documents, check items off the to-do list, send emails, or browse the web page, or browse the web, you can expect a comparable experience on all leading platforms. While Berners-Lee World Wide Web couldn't run on anything else than a Next system, its younger and much more agile offspring could. In 1991, a CERN intern, Nicola Pellow, but the line mode browser, is it built, or I think they have some errors in this article, but anyways, that traded some of World Wide Web's features for better hardware compatibility. According to the official user's guide, the line mode browser could run on almost anything, all Linux systems, VMS with any flavor of TCP/IP, VM, CMS, PC, and reusable socket library, MVS, even the Mac. So here is another CERN restoration project showcasing its capabilities. So there you go. This is the World Wide Web. This is like the first browser. Cool. Seems interesting. The NCSA and the Mosaic browser in 1993. Following Berners-Lee release of the LIP World Wide Web, the new web browser started popping up all over the world. One of the key additions to that ilk came from the direction of two programmers at the National Center for Supercomputing Applications, or NCSA, on January 23. On the 23rd of January, oh my fucking god. On the 23rd of January 1993, Mark Anderson and Eric Bina released the X-Mosaic web browser. The official release message, later redistributed by Berners-Lee himself, read, "By the power vested in me by nobody in particular, alphabet version of 0.5 of NCSA's motive-based networked information systems and World Wide Web browser, X-Mosaic is hereby released." According to the release notes, the new browser included features like multi-window support, document printing, customizable fonts, keyword search, and hotlist, which was essentially a sidebar for navigating bookmark documents. So here as well, here already it's a big improvement from this. As you can see, this was only like a terminal command line application, or at least that's what it looked like, but here now we have a GUI, we have those famous options for file edit, so on, that we have even today. We can jump forwards and backwards, we can refresh the page, we have the document title and the document URL, which all of the browsers have, and it's pretty cool. That's already a huge improvement. On the net productivity end, Mosaic offered some fledgling real-time collaboration capabilities too. Thanks to an integration with the NCSA network, it let users feed and pull documents in and out of the system. Talk about a future-proof design. So, web productivity milestone number 2 was Opera and multi-document interface. Web browsers made another step in the direction of productivity tools in 1996 when John Stephenson and von Anger Ivarsoy created Opera. That started as an internal research project for Norwegian Telenor eventually turned into an independent venture. One of the most interesting features of the Norwegian browser was support for multi-document interface browsing, an early iteration of modern browser tabs. On last year's April Fool's Day, the company joked about bringing MDI back as part of a mock vintage Opera browser, this short-lived revolution Netscape Navigator. Since the development of Mosaic was closely tied to NCSA, Mark Anderson decided to jump ship and leave the Mosaic team to start his own thing. Along with Jim Quark from Silicon Graphics, Anderson established Mosaic Communications Corporation on April 4th, 1994. It was less to a software company for sure, because he had done a hardware company, Silicon Graphics, and hardware companies are very capital intensive and they take a long time to take off, and then we basically tried to figure out what kind of software to build, and that was Mark Anderson. Along with a group of developers from the original Mosaic project, the company, later renamed to Netscape Communications Corporation, set out to improve on the original design and create what would eventually become Netscape Navigator. We have a web browser trivia. Since the new project was meant to undermine Mosaic's position, it needed a fitting code name to go with that goal. The team name settled on Mozilla, which was a combination of Mosaic and Godzilla. Read it through Mosaic Killer. Netscape Navigator. Alright, so it looks kind of similar to this, but I guess just a bit more modern with those buttons. Now they're telling you what they are. For example, here you have to guess what those arrows mean. I think in the early days of the web that wouldn't be too common knowledge, so they tell you what back and forward is, what home is, pre-what, so on and so forth. They again have the URL bar, and I don't see the page title anywhere, but they said they introduced tab browsing, but I don't see it. So Netscape was the first browser that could display partially loaded web pages. In May 1995, in the course of a partnership with Brendan Eek, Netscape also received JavaScript support that was meant to make browsing experience more dynamic. After making a big splash and gaining considerable fandom, Netscape eventually lost its dominance to Microsoft's Internet Explorer. More on that in a bit. AOL acquired the company along with its IP in 1998 and finally killed off the browser in 2008. The Internet Explorer takes off in 1995. In August, Microsoft, a latecomer to the browser party, released Internet Explorer 1.0. Internet Explorer started as a standalone product but eventually became bundled with the latest and hardly greatest Windows 95. That move marked the beginning of the end of the Netscape Navigator. When the top brass at Microsoft realized Internet Explorer had a lot of catch up to Microsoft. When the top brass at Microsoft realized Internet Explorer had a lot to catch up to, Microsoft decided to throw everything they had against Netscape's browser. The rivalry between Netscape and Internet Explorer became a key hotspot in the history of web browsers and even earned the name of the first browser war. Very epic. As noted by Jay Hoffman at the History of the Web, Netscape continued to innovate, but they knew they couldn't keep up. So in January 1998, they open sourced their browser and began giving it away for free. But even that wasn't enough. By the end of 1998, Microsoft had claimed 50% of the market. By 1999, that had risen to almost 80%. The tables had officially turned. Web productivity milestone number 3 is multi-tab browsing. Although Opera is credited with being one of the first browsers to pack multi-document interface, there is some debate about who came up with the idea of multi-tab browsing. Yes, one that lets you open, render and organize dozens of pages simultaneously. Some sources point to a relatively unknown browser called InternetWorks, released in 1994. Tabbed browsing also appeared in Netcaptor, an Internet Explorer shell created by Adam Stiles in 1997. When asked about other browsers implementing the features, Stiles admitted, "I don't remember a specific moment because it took many years, from 1997 until 2005 or so. There were Internet Explorer shells like Netcaptor, then Mozilla Firefox, followed by Opera's variant Internet Explorer. And you can see here the tabs look like folders, and those are actually folders in his favorites. He has different folders separated, and I guess those are the web pages. That's pretty cool. Or here maybe you have the browser tabs. I thought it was right here. Cool. What was that? Excite, personalize your page, free voicemail, email, calendar, address book. Interesting. Productivity wise, the invention of tab browsing was one of the pivotal moments in the history of web browsers. Not only did it speed up the process of finding and collecting information online, but it also made it possible to compare data on different sites. Tab browsing is so cool that we even included it in Taskade's desktop app. You can open up individual projects as new tabs, drag them around, so on. Hey, what's up, ASAP? Is it Tigo? Sorry if I butchered your name, brother, but what's up? Thank you for tuning in. Really appreciate you, my guy. What are you doing today? What time is it for you, actually? For me, it's 8:30 in the morning, almost. The Mozilla project takes shape, 1998. What are you building? Currently nothing. I'm just going through the Odin project and reading different articles we have on the curriculum. This is intermediate HTML and CSS. We'll be building a sign-up form, but this is after a couple of lectures. Right now I'm just reading up on the resources they provided. Alright, so the navigator was finally dethroned by Internet Explorer. Netscape decided to release the source code of the browser to the public. Netscape's intellectual property was then fed into Mozilla's project, a global community incentive that would later become a non-profit Mozilla Foundation in 2003. In 2002, the community behind the Mozilla project released two new web browsers, Mozilla and Phoenix 0.1. While the first built on Netscape's heritage and substantial financial support from the likes of AOL, the latter took a start from scratch approach. And we see how that ended. So This one I think is the first that has like icons for this type of thing. I mean, here they also had kind of like icons, but those are more modern for that time. Confusing? Don't worry, the official Phoenix 0.1 release FAQ clears it all up to some degree. Here I saw daily subscriber goal is incorrect. Daily subs right, indeed, should be daily subscriber. Yep. Well, indeed that's the case, but the thing is, I've tried Streamlabs and Stream Elements, and none of them actually work. So people subscribe and that doesn't register, and also I have alerts that don't register. So I'm going to switch that off for now, and I think I'm going to add a live sub count instead, because I can do that and it will show correctly instead of just having a blank sub go. I think that would be better. But thank you for notifying me, my man. If you subscribed, I truly appreciate you, my guy. It just doesn't alert, and I think it's a problem with YouTube. If you don't have a setting switched on that shows who you subscribe to, it will not register, and that's the case with most people on YouTube. But anyways, so question, what a bunch of videos. Why didn't they call it Mozilla Lite? Don't they know the importance of brand recognition? Third, Mozilla is not the same, it's not the name of an application, it's the name of a monolithic suite containing a browser, a mail client, an IRC client, and an indoor skating rink. We hear that's coming anyways. We also believe Mozilla in general is going in the wrong direction in terms of both and UI, and see no reason for our releases to carry those connotations. Phoenix 0.1 release notes and FAQ by Mozilla. Alright. Why don't you just try a course, for example, Udemy course or Zero to Mastery courses? Because I've tried that before, my guy, and I don't do well with tutorials or video lessons that you have to follow along or code along, because then indeed you follow the lesson, you follow the tutorial, you code along some projects and so on, but when it comes time to do something on your own, you get stuck. And that's why I like the Odin project, because they give you a lot of resources and things to read on and exercises to do, but there are hardly any video tutorials on how to build anything. There are videos explaining certain concepts and how something works, but they don't show you how to actually build it. You have to do that yourself. So that's why I like the Odin project, and I'm going through it. And they go very in detail, very in depth. I've spent more than a month now on it, and I've only finished the foundations, which was HTML, CSS and JavaScript, and I'm now on the fullstack JavaScript course. Alright, so in 2005 the Mozilla Foundation established its subsidiary, the Mozilla Corp, in order to create and distribute great, open and free of charge end-user products such as the popular Mozilla Firefox web browser and Mozilla Thunderbird email client that promote choice and innovation to the web. By August 2008, the newly renamed Firefox became the second most popular browser with market share of 32.4%, while Microsoft Internet Explorer topped the short list of key browsers with 60% of the market in hand. It was only a matter of time before Firefox on another competitor will kick it off its wobbly throne. So that was the market share in 2008. I guess Safari, Opera really down here with 2.something%. Firefox and Tascady. What is Tascady? Did you know that Tascady has its own Firefox extension? This is not okay. Anyways, Apple goes on a safari in 2003. On June 23, 2004, Apple marked another important milestone in the history of web browsers with Safari 1.0, a brand new web browser. The company wowed it as the fastest browser on the Mac, the best browser on any platform. Okay, the fastest web browser ever created for the Mac, Safari re-energizes the browser category through innovations like building Google Search Snapback to instantly return to search results, a completely new way to name, organize, and present bookmarks, tab browsing, and automatic pop-up ad blocking. Do you have a job? Are you doing this journey to become full stack in your free time? Yes, I do have a job. I'm working as a full-time COBOL mainframe developer. Oops, not this one. At a bank. I actually have work in about 30 minutes. I'm doing those streams in the morning before work or in the afternoon after work. So yeah, I'm doing it in my free time, indeed. Okay, interestingly enough, before Apple developed its own browser, the company was bound to ship its devices with Internet Explorer as a default browser. The condition was part of a 150 million conciliatory deal with the two companies struck in 1997. So this was an early version of Safari. Okay, yeah, it has the little Google search right here that Mozilla had, and maybe Chrome as well, I don't remember. Yeah, pretty cool. 2004 or 2003. After years of playing tag with its competitors, Safari has found a comfortable niche among the user base of macOS and iOS users. As of August 2020, the browser holds a respectable 17.2% of the global web browser market share. Google Chrome steals the show. It was Microsoft Internet Explorer. Was Microsoft Internet Explorer a latecomer to the browser market? Sure, but it all pales in comparison to the way Google rammed its way into the second browser war in 2008. After 2 years of development, Google unveiled its own Chrome browser on September 2nd, 2008. Branded as a fresh take on the web browser, Google Chrome actually came packed with innovative features like sandboxing tabs as individual processes, a task manager, unified search, address and history bar, web apps, or dynamic tab placement. Otherwise you can move tabs like that. On the surface was designed a browser window that is streamlined and simple. To most people, it isn't the browser that matters, it's only a tool to run the important stuff, the pages, site and applications that make up the web. It gets out of your way and gets you where you want to go. Chrome's novel functionality and exceptional user experience proved a successful combination. By August 2012, Google's browser became the alpha dog in the second browser war. 8 years later, Chrome still the champ and holds over 61% of the global browser market share. Okay. Sundar Pichai, who is the current CEO of Google, has the idea to make their own browser to compete with others, and that's the reason he's also the CEO of Google. Oh, that's really interesting. That will be interesting. I wonder what the default page will be. Alright, so Google designed Chrome to be way more than just a means of consuming content online. It made it a platform that would later turn in an entire ecosystem based on a vast marketplace of apps and extensions. all that with the support of the open source community to boot. Again, another ad, so just for context, it's pronounced Chrome. Chrome, okay. Microsoft Edge. Let me just finish up with that. The first news about Microsoft's successor to Internet Explorer started appearing in media outlets in late 2014. Nicknamed Project Spartan, Edge was meant to become the company's clean slate in the browsers market. Fast, simple, powerful, it had everything to shine, and we have to use it at work, unfortunately. Are you from Russia? No, I'm from Bulgaria, brother. Bulgaria. The new browser was officially unveiled on April 29, 2015 during Microsoft's annual Build conference. Edge was advertised as a browser built for doing, with built-in note-taking and sharing, a reading pane for no distractions, and integrations with Cortana. Who remembers Cortana? That was a huge flop in my opinion. In 2019, the browser took a bite of Chromium open source heritage and underwent a major overhaul, effectively becoming yet another web product built using Google's tech. By the end of September 2020, Edge and Internet Explorer held slightly over 6.3% of the market share. And we're finally on to the conclusion. It seems the history of web browsers had reached a peculiar point, with Chrome at the helm and no meaningful competition for. Anyways, we're likely to see the grandiose of the next browser wars anytime soon. But maybe that's not such a bad thing. After 30 years of innovation, web browsers have become an essential element of every workflow. It doesn't matter if you want to source valuable content, become more productive, or communicate with the world. Your browser's address bar holds all that and much more. Till next time. Sure. Perfect. So we've read through this article. It was quite a long one. And this is not a smaller one by any means. Oh, neighbor of Istanbul. Indeed, yeah. Are you from Turkey? That's cool. Alright, let me zoom in a little bit. Can I get rid of this thing on the left? Repos, yeah, I don't need that. Okay. I am from India. Hello, Raj. Sorry if I butchered your name, brother, but welcome to the stream and thank you for joining. Alright, so we now have how the web works, what happens behind the scenes when we type google.com in a browser. This is the table of contents, and you have a whole timeline of what happens. That will be very interesting to read. So Google's G key is pressed. When you press G, the browser receives the event and the entire autocomplete machinery kicks into high gear. Depending on your browser's algorithm and if you are in private incognito mode or not, various suggestions will be presented to you in the Dropbox below the URL bar. Most of these algorithms prioritize results based on search history and bookmarks. You are going to type google.com, so none of it matters, but a lot of code will run before you get there and the suggestions will be refined with each key press. It might even suggest google.com before you type it. Alright, you hit enter. So to pick a 0 point, let's choose the enter key on the keyboard, hitting the bottom of its range. At this point, an electrical circuit specific to the enter key is closed, or key down is pressed basically. Either directly or capacitively, this allows a small amount of current to flow into the logic circuitry of the keyboard, which scans the state of each key switch. debounces the electrical noise of the rapid intermittent closure of the switch and converts it to key code integer, in this case 13, this probably ASCII. The keyboard controller then encodes the key code for transport to the computer. This now almost universally over a universal serial bus or USB or Bluetooth connection. In case of the USB keyboard, the key code generated is stored by internal keyboard circuitry memory in a register code endpoint. The host USB controller pulls that endpoint every 10 milliseconds, so gets the key code value stored in it. The value goes into the USB SIE or serial interface engine, sent at a maximum speed of 1.5 megabytes per second. This serial signal is then decoded at the computer's host USB controller and interpreted by computer's human interface device. Universal keyboard device driver. The value of the key is then passed to the operating system's hardware abstraction layer. In the case of touchscreen keyboards, so on mobile I guess, when the user puts their finger on a modern capacitive touchscreen, a tiny amount of current gets transferred to the finger. This completes the first circuit through the electrostatic field of the conductive layer and creates a voltage drop at that point of the screen. The screen controller then raises an interrupt reporting the coordinate of the click. Then the mobile OS notifies the current focused application of a click event in one of its GUI elements, which is now the virtual keyboard application buttons. The virtual keyboard can now raise a software interrupt for sending a key pressed message back to the OS. The interrupt notifies the current focused application of a key pressed event. Alright, so that was pretty interesting how that worked. I've imagined it all in my head. So after that, we parse the URL. The browser now has the following information contained in the URL or uniform resource locator: the protocol, HTTP, use hypertext transfer protocol, resource, how do you say it, a slash, retrieve main index page. When no protocol or valid domain name is given to the browser, proceeds to feed the text given in the address both to the browser's default web search engine. Check HSTH list. This is deprecated, so I'm not going to read through this. Note: website can still modern web browsers. Yeah, so I don't know what HSTH is, and it's hard for me to. The browser check its preloaded HTTP strict transport security list. This is a list of websites that have requested to be contacted via HTTPS only. If the website is in the list, the browser sends its request via HTTPS instead of HTTP. Otherwise, the initial request is only sent via HTTP. Note: the website can still use HSTH policy without being in the HTA list. Anyways, fuck that, I'm not reading through that. DNS lookup. The browser tries to figure out the IP address of the entered domain. The DNS lookup proceeds as follows: browser cache. The browser caches DNS records for some time. Interestingly, the OS does not tell the browser the time to live for each DNS record, and so the browser caches them for a fixed duration, varies between browsers 2 to 30 minutes. You have OS cache. If the browser cache does not contain the desired record, the browser makes a system call, get host by name in Windows. The OS has its own cache, router cache. The request continues onto your router, which typically has its own DNS cache, ISP DNS cache. The next place checked is the cache ISP's DNS server with the cache naturally. Recursive search. Your ISP's DNS server begins a recursive search from the root name server through the .com top level name server to Google's name server. Normally, the DNS server will have names of the .com name servers in cache, and so a hit to the root name server will not be necessary. Here is a diagram of what a recursive DNS search looks like. So you have the DNS iterator, and it says where is wikipedia.org, and it searches the root name server, the .org name server, and then it finds Wikipedia. Interesting. Okay. One worrying thing about DNS is that the entire domain, like wikipedia.org or facebook.com, seems to map to a single IP address. Fortunately, there are ways of mitigating the bottleneck. Round-robin DNS is a solution where the DNS lookup returns multiple IP addresses rather than just one. For example, face.com actually maps to 4 IP addresses. Load balancer is the piece of hardware that listens on a particular IP address and forwards the request to other servers. Major sites will typically use expensive high-performance load balancers. Geographic DNS improves scalability by mapping a domain name to different IP addresses depending on the client's geographic location. This is great for hosting static content so that different servers don't have to update shared state. Anycast is a routing technique where a single IP address maps to multiple physical servers. Unfortunately, Anycast does not fit well with TCP and is rarely used in this scenario. Most of the DNS servers themselves use Anycast to achieve high availability and low latency of the DNS lookups. Users of Anycast service DNS is an excellent example. Will always connect to the closest from a routing protocol perspective DNS server. This reduces latency as well as providing a level of load balancing, assuming that your customers are evenly distributed around your network. Okay. Next we have opening a socket plus TLS handshake. Once the browser receives the IP address of the destination server, it takes that and the given port number from the URL. The HTTP protocol defaults to 80 and the HTTPS protocol defaults to port 443, and makes a call to the system library function named socket and requests TCP socket stream. The client computer sends a client hello message to the server with its TLS version, list of cipher algorithms and compression methods available. The server replies with server hello message to the client with the TLS version, selected cipher, selected compression methods at the server's public certificate signed by CA or certificate authority. The certificate contains a public key that will be used by the client to encrypt the rest of the handshake until a symmetric key can be agreed upon. The client verifies the server's digital certificate against its list of trusted certificate authorities. If trust can be established based on the CA, the client generates a string of pseudo random bytes and encrypts this with the server's public key. These random bytes can be used to determine the symmetric key. The server decrypts the random bytes using its private key and uses these bytes to generate its own copy of the symmetric master key. the client sends a finished message to the server, encrypting a hash of the transmission. Up to this point, with the symmetric key, the server generates its own hash and decrypts the client sent hash to verify that it matches. If it does, it sends its own finished message to the client, also encrypted with the symmetric key. From now on, the TLS session transmits the application HTTP data encrypted with the agreed symmetric key. Alright, so now we are onto the HTTP protocol. Right, anyways, you can be pretty sure that dynamic sites such as Facebook, Gmail will not be served from the browser's cache because dynamic pages expire either very quickly or immediately, expiry date set to past. If the web browser used was written by Google, instead of sending an HTTP request to retrieve the page, it will send a request to try and negotiate with the server an upgrade from HTTP to SPDY protocol. Know that SPDY is being deprecated in favor of HTTP 2 in latest version of Chrome. So in HTTP you send a GET request for google.com. You get an accept with some headers, user agent, this is the browser, accept encoding gzip, host google.com, cookies, so on. Alright. We have quite a bit to read, but HTTP server response. The GET request names the URL to fetch google.com. The browser identifies itself user agent header and states what types of response it will accept and accept encoding headers. The connection header asks the server to keep the TCP connection open for further requests. The request also contains the cookies that the browser has for its domain. As you probably already know, cookies are key value pairs that track the state of a website in between different page requests, and so the cookies store the name of the logged in user, a secret number that was assigned to the user by the server, some sort of user settings, etc. The cookies will be stored in a text file on the client and set to the server with every request. HTTP 1.1 defines the close connection option for the sender to signal that the connection will be closed after a completion of the response. For example, connection close. After sending the request and headers to the web browser, sends a single blank new line to the server indicating that the content of the request is done. Under server response with a response code denoting the status of the request, and response with the response of the form 200, which is OK, followed by a single new line, and then sends a payload of the HTML content of google.com. The server might then either close the connection, or if the header sent by the client requested it, keep the connection open to be reused for further requests. If the HTTP header sent by the browser included sufficient information for the web server to determine if the version of the file cached by the web browser has been unmodified since the last retrieval. In example, if the web browser included an e-tag header, it may instead respond with a request in the form of 3 or 4 not modified response headers and no payload, and the browser instead retrieves the HTML from its cache. After parsing the HTML, the browser and server repeats this process for every resource, image, CSS, favicon, etc. referred to by the HTML page except instead of get HTTP1, the request will get at URL relative to google.com. Okay, if the HTML referenced a source on a different domain than google.com, the web browser goes back to the steps involved in resolving the other domain and follows all steps up to that point for that domain. The host reader in the request will be sent to the appropriate server and name instead of google.com. So the trailing slash in the URL, for example, facebook.com and trailing slash is important. In this case, the browser can safely add the slash for URLs of the form example.com folder or file. The browser cannot automatically add a slash because it is not clear whether folder or file is a folder or file. In such cases, the browsers will visit the URL without the slash, and the server will respond with a redirect, resulting in an unnecessary round trip. Okay, the server might respond with a 301 moved permanently respond to tell the browser to go to google.com instead, or google.com without the World Wide Web. There are interesting reasons why the server insists on the redirect instead of immediately responding with the web page that the user wants to see. One reason has to do with search engine rankings. See if there are two URLs for the same page. Search engines might consider them to be two different size, each with fewer incoming links and thus a lower ranking. Search engines understand permanent redirects and will combine the incoming links from both sources into a single ranking. Also, multiple URLs for the same content are not cache friendly. When a piece of content has multiple names, it will potentially appear multiple times in caches. Note: HTTP response starts with the returned status code from the server, following a very brief summary of that status code denotes. So I know about those. 100 something is informational, 200 is successful, 3 something is redirect, 4 something is error on the client part, and 500 something is error on the server's part. Alright. I have to take a quick break since I've been reading for an hour and non-stop, so where are we? Alright, here. So I'm going to take a 10-minute break and be right back. Alright, I'm back. I had to rest for a second, but we continue onwards with the HTTP server request handle. The HTTPD or HTTP daemon server is the one handling requests and responses on the server side. The most common HTTPD servers are Apache or NGX for Linux and IIS for Windows. The HTTP daemon receives the request. The server breaks down the request to the following parameters: HTTP request method, either get, post, get, put, or delete. In the case of a URL entered directly into the address bar, this will be get. Domain, in this case google.com. Requested path or page, in this case / as no specific path or page is requested. And the server verifies there is a virtual host configured on the server that corresponds with google.com. The server verifies that google.com can accept GET requests. The server verifies that the client is allowed to use this method by IP authentication, etc. If the server has a rewrite module installed, like mod rewrite or Apache or for Apache or URL rewrite for IIS, it tries to match the request against one of the configured rules. If a matching rule is found, the server uses that rule to rewrite the request. The server goes to pull the content that corresponds with the request. In our case, it will fall back to the index file, as the / is the main file. The server parses the file according to the request handler. A request handler is a program in ASP.NET PHP Ruby that reads the request and generates HTML for the response. If Google is running on PHP, the server uses PHP to interpret the index file and streams the output to the client. Note, one of the interesting difficulty that every dynamic website faces is how to store data. Smaller sites will often have a single SQL database to store their data, but sites that store a large amount of data and or have many visitors have to find a way to split the database across multiple machines. Solutions include sharding, splitting up a table across multiple databases based on the primary key, or also partitioning of tables, replication and usage of simplified databases with weakened consistency semantics. So the server response, the entire response, it's 36 kilobytes, the bulk of them in the byte blob at the end that I trimmed. So most of the responses are this trimmed part right here. The content encoding header tells the browser that the response body is compressed using the gzip algorithm. After decompressing the blob, you see the HTML you'd expect. Okay. Notice the header that sets content type to text and HTML. The header instructs the browser to render the response content as HTML instead of, say, downloading it as a file. The browser will use the header to decide how to interpret the response, but will consider other factors as well, such as the extension of the URL. Behind the scenes of the browser, once the browser server supplies the resources, HTML, CSS, JavaScript, images, etc. to the browser, it undergoes the below process: parsing HTML, CSS and JavaScript, rendering, construct the DOM tree, render tree, layout of render tree, painting the render tree. The browser's high-level structure, user interface includes the address bar, back and forward button, bookmarking menu, etc. Every part of the browser display except the window where you see the requested page. Browser engine marshals action between the UI and the rendering engine. Rendering engine responsible for displaying the requested content. For example, the rendering engine parses HTML and CSS and displays the parsed content on the screen. Networking for network calls such as HTTP requests using different implementations for different platforms behind a platform independent interface. UI backend used for drawing basic widgets like combo boxes and windows. The backend exposes a generic interface that is not platform specific. Underneath it uses operating system's user interface methods. JavaScript engine interpreter is used to parse and execute JavaScript code. Data storage, this is a persistence layer. The browsers may need to save data locally, such as cookies. Browsers also support storage mechanisms such as local storage, IndexedDB, and file system. Okay, let's start with the simple possible case, a plain HTML page with some text and single image. What does the browser need to process this simple page? First is conversion. The browser reads the raw bytes of the HTML of the disk or network and translates them to individual characters based on the specific encoding of the file. Example, UTF-8. Tokenizing. The browser converts strings of characters into distinct tokens specified by the W3C HTML5 standards. Example is the comma and other strings within the angle brackets. Each token has a special meaning and set of rules, so each element of the HTML. Lexing. The emitted tokens are converted into objects which define their properties and rules. DOM construction. Finally, because the HTML markup defines relationships between different tags, some tags are contained within tags. The created objects are linked to a tree data structure that also captures the parent-child relationships defined in the original markup. HTML object is a parent of the body object, the body is a parent of the paragraph object, and so on. Alright, so the HTML structure or the document object model basically shown as a tree. The final output of this entire process is the document object model or the DOM of our simple page, which the browser uses for all further processing of the page. Every time the browser has to process HTML markup, or it has to step through all the steps above, convert bytes to characters, identify tokens, convert tokens to nodes, and build the DOM tree, this entire process can take some time, especially if you have a large amount of HTML to process. Okay, this is like a network request to parse the HTML. If you open Chrome DevTools and record a timeline while the page is loaded, you can see the actual time taken to perform this step. In the example above, it took us 5 milliseconds to convert a chunk of HTML bytes into a DOM tree. Of course, if the page was larger, as most pages are, this process might take significantly longer. You see this in our future sections on creating smooth animations, that this can easily become your bottleneck if the browser has to process large amounts of HTML. Rendering engine. A rendering engine is a software component that takes marked up content such as HTML, XML, image files, etc., and formatting information such as CSS, HSL, etc., and displays the formatted content on the screen. And we have different engines for different browsers. I don't see V8, but maybe that's something else. WebKit is an open source. It's strange that it's open source, it's Apple's after all. But WebKit is an open source rendering engine which started as an engine for the Linux platform and was modified by Apple to support Mac and Windows. The rendering engine is single-threaded. Almost everything except networking operations happens in a single thread. In Firefox and Safari, this is the main thread of the browser. In Chrome, it's the tab process main thread. Network operations can be performed by several parallel threads. The number of parallel connections is limited, usually 6 to 13 connections per hostname. The browser main thread is an event loop. It is an infinite loop that keeps the process alive. It waits for events like layout and paint events and processes them. Note, browsers such as Chrome run multiple instances of the rendering engine for each tab. Each tab runs in a separate process. Okay. The main flow. The rendering engine will start getting the contents of the requested document from the networking layer. This is usually done in 8 kilobyte chunks. After the basic flow of the rendering engine is, after that, parsing the HTML to construct the DOM tree, render tree construction, layout of the render tree, painting the render tree. The rendering engine will start parsing the HTML document and convert elements to DOM nodes in a tree called the content tree. The engine will parse the style data both in external CSS file and in style comment. Styling information together with visual instructions in the HTML will be used to create another tree, the render tree. The render tree contains rectangles with visual attributes like colors, dimensions. The rectangles are in the right order to be displayed on the screen. After the construction of the render tree, it goes through a layout process. This means giving each node the exact coordinates where it should appear on the screen. The next stage is painting the render tree. The next stage is painting. The render tree will be traversed and each node will be painted using the UI backend layer. It's important to understand that this is a gradual process for better user experience. The rendering engine will try to display contents on the screen as soon as possible. It will not wait until all HTML is parsed before starting to build and lay out the render tree. Parts of the content will be parsed and displayed while the process continues with the rest of the contents that keeps coming from the network. Given below is WebKit's flow. Okay, we have parsing basics. Parsing, translating the document to a structure the code can use. The result of parsing is usually a tree of nodes that represent the structure of the document. Grammar parsing is based on syntax rules the document obeys, the language or format it was written in. Every format you can parse must have deterministic grammar consisting of vocabulary and syntax rules. It's called a context-free grammar. Parsing can be separated into two sub-processes, lexical analysis and syntax analysis. Lexical analysis is the process of breaking the input into tokens. Tokens are the language vocabulary, the collection of valid building blocks, and syntax analysis is the applying of the language syntax rules. Parsers usually divide the work between the two components, the lexer that is responsible for breaking the input into valid tokens and the parser that is responsible for constructing the parse tree by analyzing the document structure according to the language syntax rules. The lexer knows how to strip irrelevant characters like the white spaces and line breaks. Okay, the parsing process is iterative. The parser will usually ask the lexer for a new token and try to match the token with one of the syntax rules. If a rule is matched, a node corresponding to the token will be added to the parse tree and the parser will ask for another token. If no rule matches, the parser will store the token internally and keep asking for tokens until a rule matching all the internally stored tokens is found. If no rule is found, then the parser will raise an exception. This means the document was not valid and contained syntax errors. The job of the HTML parser is to parse the HTML markup into a parse tree. HTML definition is in D2D, or document type definition format. This format is used to define languages of the SGML family. The format contains definitions for all allowed documents under attributes and hierarchy. As we saw earlier, the HTML D2D doesn't form a context-free grammar. HTML parsing algorithm consists of two stages, tokenization and tree construct. Tokenization is the lexical analysis, parsing the input into tokens. Among HTML tokens are start tags, end tags, attribute names, attribute values. The tokenizer recognizes the token, gives it to the tree constructor, and consumes the next character for recognizing the next token, and so on until the end of the input. Alright, we have the DOM tree, the output tree. The parse tree is a tree of DOM element and attribute nodes. DOM is short for document object model. It is the object presentation of the HTML document and the interface of the HTML elements to the outside world like JavaScript. The root of the tree is the document object. The DOM has an almost one-to-one relation to the markup. For example, hello world. Alright, this markup would be translated to the following DOM tree. Why is the DOM slow? The short answer is that the DOM is not slow. Adding and removing a DOM node is a few pointer swaps, not much more than setting a property on the JS object. However, layout is slow. When you touch the DOM in any way, you set a dirty bit on the whole tree that tells the browser it needs to figure out where everything goes. Again, when JS handles control back to the browser, it invokes its layer algorithm, or more technically, it invokes its CSS recalc algorithm, then layout, then repaint, then recompositing to redraw the screen. The layout algorithm is quite complex. Read the CSS spec to understand some of the rules, and that means it often has to make non-logical decisions. Worse layout is triggered synchronously by accessing certain properties. Among those are get computed style value, get bounding client width, set offset width, offset height, etc., which makes them so stupidly easy to run into. Full list is here. Because of this, a lot of Angular and jQuery code is stupidly slow. One layout will blow your entire frame budget on a mobile device. When I measured Google Instant in 2013, it caused 13 layouts in one query and walked up the screen for nearly 2 seconds on a mobile device. It's since been sped up. React doesn't help speed up layout. If you want butter smooth animations on a mobile web browser, you need to resort to other techniques like limiting everything you do in a frame to operations that can be performed on the GPU. But what does it do is ensure that there is at most one layout performed each time you update the state of the page. That's often quite an improvement from the status quo. Alright. Render tree. While the DOM tree is being constructed, the browser constructs another tree, the render tree. This tree is of visual elements in the order. This tree is of visual elements in the order in which they will be displayed. It is the visual representation of the document. The purpose of this tree is to enable painting the contents in their correct order. A renderer knows how to lay out and paint itself and its children. Each renderer represents a rectangular area, usually corresponding to a node CSS box. Okay. The renderers correspond to DOM elements, but the relation is not one-to-one. Non-visual DOM elements will not be inserted in the render tree. An example is the head element. Also, elements whose display value was assigned to none will not appear to the tree, whereas elements with hidden visibility will appear in the tree. There are DOM elements which correspond to several visual objects. There are usually elements with complex structure that cannot be described by a single rectangle. For example, the select element has 3 renderers, one for the display area, one for the drop down list box, and one for the button. Also, when text is broken into multiple lines, because the width is not sufficient for one line, the new lines will be added as extra renderers. Some renderer objects correspond to a DOM node but not in the same place in the node. Floats and absolutely positioned elements are out of flow, placed in different parts of the tree and mapped to the real frame. A placeholder frame is where they should have been. In WebKit, the process of resolving style and creating a renderer is called an attachment. Every DOM node has an attach method. Attachment is synchronous. Node insertion to the DOM tree calls the new node attach method. Building the renderer tree requires calculating the visual properties of each renderer object. This is done by calculating the style properties of each element. The style includes the style sheets of various origins, inline style elements, and visual properties in the HTML, like the background color property. The latter is translated to matching CSS style properties. CSS parsing. Alright, CSS selectors are matched by the browser engines from right to left. Keep in mind that when a browser is doing selector matching, it has one element, the ones it's trying to determine the style for, and all your rows and their selectors, and needs to find which rows match the element. This is different from the usual jQuery things, say, where you only have one selector and you need to find all of the elements that match that selector. A selector specificity is calculated. We know about the specificity, so we'll skip that. Concatenating the 3 numbers A, B, C, and D. Alright, this is how you calculate it. WebKit uses a flag that marks if all top level styles, including imports, have been loaded. If the style is not fully loaded when attaching, placeholders are used and it's marked in the document, and they will be recalculated once style sheets were loaded. Alright. So we have layout and painting and trivia for last, but we're not going to do a trivia, so last 2 are layout and painting. When the renderer is created and added to the tree, it does not have a position and size. Calculating these values is called layout or reflow. HTML uses a flow-based layout model, meaning that most of the time it is possible to compute the geometry in a single pass. Elements later in the flow typically do not affect the geometry of elements that are earlier in the flow, so layout can be preceded left to right, top to bottom. Throughout the document, the coordinate system is relative to the root frame. Top and left coordinates are used. The layout is a recursive process. It begins at the root renderer, which corresponds to the element of the HTML document. Layout continues recursively throughout some or all of the frame hierarchy, computing geometric information for each renderer that requires it. The position of the root renderer is 0.0 and its dimensions are the viewport, the visual part of the browser windows, All renderers have a layout or reflow method. Each renderer evokes the layout methods as of its children that need layout. In order to do a full layout for every small change, browsers use a dirty bit system. A renderer that is changed or added marks itself and its children as dirty, needing layout. There are two flags, dirty and children are dirty, which means that although the renderer itself may be okay, it has at least one child that needs a layout. The layout usually has the following pattern. Parent renderer determines its own child, its own width. Parent goes over child and plays the child renderer, so it sets it as X and Y. Calls the child layout if needed. There are calls child layout if needed. They are dirty or wearing global layout for some other reason, which calculates the child's height. Parent uses children's cumulative heights and the heights of margins and padding to set its own height. This will be used by the parent's renderer's parent. Sets dirty bit to false, so after it renders it, it sets it to false. Sure. Also note, layout trashing is where a web browser has to reflow or repaint a web page many times before the page is loaded. In the days before JavaScript prevalence, websites were typically reflowed and painted just once, but these days it's increasingly common for JavaScript to run on page load, which can cause modifications to the DOM and therefore extra reflows or repaints depending on the number of reflows and complexity of the web page. There is a potential to cause significant delay when loading the page, especially on lower powered devices such as mobile phones or tablets. And finally, lastly, we have painting. Oh, my head is going to explode from all this reading. Alright, in the painting stage, the renderer tree is traversed and the renderer's paint methods its code to display content on the screen. Painting uses the UI infrastructure component. Like layout, painting can also be global, the entire tree is painted, or incremental, the incremental painting. In incremental painting, some of the renderers change in a way that does not affect the entire tree. The changed renderer invalidates the rectangle on the screen. This causes OS to see it as a dirty region and generate a paint event. The OS does it cleverly and coalesce. Anyways, before repainting, WebKit saves the old rectangle as a bitmap. It then paints only the delta between the new and old rectangles. The browsers try to do the minimal possible actions in response to a change, so changes to an element color will cause only repaint of the element. Changes to the element position will cause layout repaintment of the element and its children and possibly siblings. Adding a DOM node will cause layout and repaint of the node. Major changes like increasing font size of the HTML element will cause invalidation of caches, relayout, and repaint of the entire tree. Okay. There are three different positioning schemes. Normal, the object is positioned according to its place in the document. This means its place in the renderer tree is like its place in the DOM tree and laid out according to its box type and dimensions. Float, the object is first laid out like normal float and moved as far to the left or to the right as possible. Absolute, the object is put in the renderer tree in a different place than in the DOM tree. The positioning scheme is set by the position property and the float attribute. Static and relative cause a normal flow. Absolute, fixed, and I guess sticky cause absolute positioning. So in the static positioning, no position is defined and the default positioning is used. In the other schemas, the author specifies the position top, bottom, left and right. Layers are specified by the z-index property. It represents the third dimension of the box, its positioning along the z-axis. The boxes are divided into stacks called stacking context. In each stack, the back elements will be painted first and the forward elements on top, closer to the user. In case of overlap, the foremost element will hide the former element. These stacks are ordered according to the z-index property. Boxes with z-index property form a local stack. Alright, so we're done with that. It was fucking huge. Lastly, we have the trivia, but I'm not going to bother with that, so we mark this as complete and we can move on to the next lesson, which we'll tackle either later today or tomorrow morning. I'm going to end the stream for now, so thank you guys for tuning in, truly appreciate you, and until next time, bye bye.